Here's kind of a standard satellite question. If you're given a height above Earth and a mass, we should be able to figure out its time period, its velocity, and its total energy. In this particular one, the height above Earth is given. The satellite's quite far away, 28,500 kilometers. The height is given as the distance above Earth, so this is what's given in the question. We've worked through a few of these in class, but a key we have to remember is that the radius that we need to plug into our physics equations is always the radius of Earth, or whatever planet the question is about, plus the height. It's always the center to center distance. So for a question like this one, where we're given the height, we need to take the radius of the Earth. You don't have to memorize any numbers. The radius of the Earth is 6.38 times 10 to the 6 meters, and add on the height. In this case, the height I made up was 28,500 kilometers. We have to have consistent units before we can add. I like putting things in times 10 to the 6 to match the radius of the Earth. So 28,000 kilometers, a kilo means 1,000. That's the same as 28,500,000 meters. Or if I write that a little bit differently, the height was 28.5 times 10 to the 6 meters, and the radius of the Earth is 6.38 times 10 to the 6 meters. If we line them up, if we add them that way, then it's kind of elementary math. We can just add them up. We get an 8 back here. The 5 and the 3 make another 8. Oops. The 6 and the 8 make a 14. Carry the 1, we get 34.88 times 10 to the 6 meters. That's the R value that we'll have to use in our equations. That's kind of the first step before we can get anywhere with this question. We need to know the distance from center to center. What's kind of cool about satellites is they're based on centripetal motion. Satellites are going in a circle around the Earth. Since they're going in a circle, the A turns into V squared over R. The force that's making them go in a circle is the force of gravity, GMM over R squared. If we clean that up, one of the M's cancels, one of the R's cancels, and we get the equation that V squared equals GM over R. I'm going to put a star beside that because we use that in other places as well. For this particular question, that was one of the things we were asked for, was the speed of the satellite given its mass and how high it is. So we've already got enough that we can figure out the speed. V squared equals, instead of G, 6.67 times 10 to the negative 11. The mass in this case is Earth, 5.98 times 10 to the 24 when we're in kilograms. And the radius, that's what we figured out before, that was that 34.88 number. You don't have to keep it as a times 10 to the 6, that's just a habit I got into. You could put it in regular standard notation of 3.488 times 10 to the 7, just whatever works. You can play their calculator, double check, but when I did it, I got that the speed after square rooting was 3380 meters per second. In the question, we were also asked to find the time period. There's a couple ways to get the time period. Since we have the speed, we know that V is 2 pi r over time period. It does a full circumference in one time period. Since we have the speed, we could just use that. We know the R value, we could rearrange for time. Just to show in this case it would be a longer way, but just to remind you of another way to do it, that star, we know that V squared is GM over R. So if we take our speed, our 2 pi r over time period, and square it, that's equal to GM over R. When we clean that up, we get a 4, we get a pi squared, we get an r squared, and then the r on the denominator on the other side makes that an r cubed. The GM is still there, and if I flip the t to the numerator, we get a t squared on the right. This is a cool equation that connects radius to time period. In this one, we know everything but the time period. So if we rearrange, t squared is 4 pi squared, the r number cubed. The r was that 3488 number, 34.88. Times 10 to the 6, we have to cube that number. And then to get t squared all by itself, we have to divide by 6.67 times 10 to the negative 11. And the mass of Earth, 5.98 times 10 to the 24. I'll let you double check. It's just a lot of calculator work. Watch your brackets when you're squaring scientific notations and dividing two numbers. But after square rooting, you should get a time period of approximately 64,800 seconds. It's fine to leave it like that, but just to make it more convenient, if we convert it, that's 18 hours. The last part of this question that I made up was to find the energy the satellite has. Whenever anything's far from Earth and we need to know the total energy is always the kinetic energy plus the gravitational. Kinetic energy is always 1/2 mv squared. Gravitational energy is always negative gmm over r. So the plus of the EG turns into a subtraction, negative gmm over r. That start equation we came up with a while ago, for a satellite, we know that v squared is gm over r. So our total energy equation for a satellite, we can substitute, and we get kind of a new cool equation, 1/2 m, and then the v squared was gm over r. From that, we're going to take away gmm over r. It looks a little bit funny, but if I sort of rewrite it and clean it up, we have 1/2 gmm over r. If I just flip the order of that numerator, and then we're going to subtract a gmm over r. That one we can clean up. We have 1/2 gmm over r minus a full gmm over r. That ends up being negative 1/2 gmm over r. This is an equation that's in terms of the r value that was given, or that we figured out from the height given in the question, so we can just plug in our constants and crunch it out. The g is always 6.67 times 10 to the negative 11. It's orbiting Earth, so our 598 number goes in. In the question, I made up a mass of the satellite. You can scroll back and see I made up a 100 kilogram satellite, so 100 on the numerator. The r value was that 3488 for this question. All right, more calculator time. If you crank that out, watch your 1/2, watch your order of operations. There's a negative involved, so our final answer is going to be negative 5.7 is what I got, times 10 to the 8 joules. Sometimes we talk about binding energy. That satellite is bound to Earth. It's not going to leave unless we add energy to it. The amount of energy we would need to add is that exact same number, that 5.7 times 10 to the 8. So if asked, this question didn't, but if asked, the binding energy is always the absolute value of the total energy. In this case, that would just be the plain old 5.7 times 10 to the 8 joules.